This is an electric potential problem. It reads, a thin spherical shell made of plastic carries a uniformly distributed negative charge, negative Q1, and a thin circular disc made of glass carries a uniformly distributed positive charge, positive Q2. The radius R1 of the plastic spherical shell is very small compared to the large radius R2 of the glass disc. The distance from the surface of the spherical shell to the glass disc is d, and d is much smaller than R2. Find the potential difference of V2 minus V1. So I have a picture drawn here of the shell, and this is the glass disc next to it. And you can see they're pretty close together. This is the distance d apart. And this is the initial location 1. And it's inside, directly in the middle of the shell. And location 2, right here, is right outside the surface of the disc. And that's the final location. So you can see that the path is a straight line from 1 to 2. So knowing that, we can use the superposition principle to find the electric field, the net electric field, and that's just going to be the electric field of the shell plus the electric field of the disc. And so from knowing the equation for the potential difference, we know we can integrate the negative integral from 1 to 2, and that's the E net times dl. And so if we take this E net, we can plug it in and do the individual electric fields times their displacements and add them together to find the potential difference. So I've redrawn the picture here and drawn the electric fields due to the disc and the shell. And we know inside of the shell, the electric field is going to be 0. And here I've drawn the electric field due to the shell. And here you can see the magnitude's a little bit smaller as it gets closer towards the shell. It's greater, and then the electric field for the disc is pointed outwards all along this path away from the disc, because these positive charges are going to attract to this negative sphere here. So the potential difference due to the shell, since we put the origin at the center of the shell, we know that it's going to be 0 because the electric field inside the shell is 0. So we can write it like this. The electric field due to the shell is just going to be in the x direction because that's the only direction it's going along the x plane. It's 1 over 4 pi epsilon naught negative Q1 over x squared. And because we've established that the electric field for the shell is 0, it's just going to have the displacement, which is dx 0, 0. And so then we can find V2 minus V of the surface of the shell. And we're going to have to integrate from R1, the radius, over here, which I've shown as right here. That's the radius due to the spherical shell. And then we're going to do R1 plus D. So that's this plus D. So we integrate this, which is the electric field due to the shell, for dx, and this is what we get. And that's basically V2 minus V1 for the to find the electric field due to the shell. So that's just one component for the shell. And then we do it for the disc, and because D is much smaller than R2 and R1 is much smaller than R2, we can assume that the electric field for the disk is equal to this, which is just a known equation. And then we can also assume, because the disk is uniform, the electric field is going to be uniform all across the disk. So V2 minus V1 is therefore just this times R1, the radius of the sphere, plus D. So then we just add those two up, delta V due to both the shell and the disk.